So let's look at this example of inherited stature. This is Galton's data set in which he's trying to predict mid-parental height, he's trying to predict children's height based on mid-parental height. So he kind of had this funky variable in which he combined your mom's height and your dad's height into a single variable. But let's improve on what Galton did. Let's treat heights separately, right? Let's use your father's height and your mother's height as separate variables, as separate inputs into a regression model to predict the height of children. This is our simple linear regression output. Right? This is just using father's height. Right? So simple linear regression model, right? We get an intercept and we get a slope for father. Okay? The regression model just using father's height, this is simple linear regression. We have an intercept of 39 roughly, and we have a slope of 0.40. For every 1 inch increase of your father's height, we expect the height of children to increase by 0.4. When your father is 0 inches tall, we expect you to be 39 inches tall, roughly, which of course is not a sensible interpretation. That's one thing you have to be careful about the intercept. It's not always substantively meaningful because it's not always substantively meaningful to set your inputs to 0. Everybody has parents with some height, not just 0 inches. But the point here is that this is a simple linear regression model. A multiple linear regression model would include mother's height as well. So this is a multiple linear regression model. The output is really the same, okay? The residuals, we have a call, the format of the output. The residuals will be different. The intercept and slopes will be a little bit different, t-values, but the overall format of the output is the same. We just see that there's another row such that we have an intercept, but we also have the slope of fathers and the slope of mothers. Okay? The idea here is that we're predicting children's height using the height of their fathers and the height of their mothers. The model is now 22 roughly plus 0.38 times the height of fathers plus 0.28 times the height of mothers. So we can see that the coefficient of father has changed because it now has a different meaning. What it's telling us now is that the slope of father is for every 1 inch increase in father's height, we expect children's height to increase by 0.38 inches, holding constant or controlling for mother's height. In a similar way, we can say that the partial regression coefficient, that partial slope for mother, is interpreted as follows. For every 1 inch increase of the height of a mother, the children's height is expected to increase by 0.28 inches, holding constant or controlling for the height of fathers. We can't just say, it would be incorrect to say, for every 1 inch increase of your father's height, the height of children will increase by 0.38 inches. That's incorrect because that is not what it's telling us. It's telling us for every 1 inch increase of father's height, we expect the children's height to increase by 0.38 inches, holding constant or controlling for mother's height. Right? It's key that you talk about the fact that you're controlling or holding constant this other variable. Right? So we can also see here that the intercept, right, it's when both variables are set to 0. The intercept, is interpreted as follows. If your mother is 0 inches tall, if your father is 0 inches tall, then the model we predict that the height of children will be 22.31 inches. It's again not sensical because everybody has parents of at least 1 inch tall, I would hope. But the important part here is that the intercept, the interpretation is a little bit different. It's when all inputs are equal to 0. We're going to continue this example in just a moment.